The most common kind of linkage mechanism you'll encounter has 4 bars in it, so it's called a 4-bar linkage. And in a 4-bar linkage, there's one bar that is fixed, and you might call that the ground link, and often it's at the bottom. One of them is the driver, so picture that attached to something that turns, could be a motor, for example. That's the driver or the crank. There's another one that follows along with that, the follower. And then between the crank and the follower is a connecting link, the connector or the coupler. Now, it's kind of interesting that the motion that these various links follow depends on the relative lengths of each of them. Which one is shorter, which one is longer, will affect what kind of motion you can get out of these things. So, for example, if the crank and the follower are the same length, you have essentially a parallelogram then, don't you? And in that situation, where they're both the same length, both the crank and the follower will rotate in a full circle. And you can see examples of these all over the place. Here's a picture I took of a basketball hoop on Hilliard Street that has one of those parallel linkages. Hinges in a toolbox have that. Here's one in an excavator. So those are all dual crank mechanisms where the bars are parallel. If the shortest link and the next shortest length are moving, so the shortest link will be the crank and the follower will be the next shortest link, that's called a crank and rocker. And when you have that kind of proportion, the crank still turns in a full circle, and the follower cannot turn in a full circle. It oscillates back and forth. And again, like in all 4-bar linkages, the crank and the follower are connected by this coupler, this linking rod. Here's a schematic of that situation. So here's the crank and its circular path, and here's the follower rocking back and forth. You see examples of these in car engines again. Also windshield wipers. The drag link is a weird one, I think. In the drag link, the ground link, the one that's fixed, is the shortest link, and the coupler is the next shortest link, and the crank and the follower are the longest links. Well, what happens when you have that kind of situation where the crank and the follower are the longest is that the crank turns in a full circle and the follower also turns in a full circle, but it's not a constant speed. And if you look in the notes field of this PowerPoint slide, I have put a link there that you can click on where you can go look at an animation of one of these. So here's what a schematic would look like. Then if the connecting link is the shortest one and the ground link is the next shortest one, and then the crank and the follower are the longest, then both the crank and the follower oscillate back and forth. And here I picture windshield wipers moving together, although that's not technically a dual rocker. Finally, we have a slider crank, and this is what you see in a classic locomotive wheel. So in this photograph, the crank is actually the solid piece between the axle of that wheel and where the slider connects. That's the crank. And then the slider, the solid bar, moves back and forth. So this is a mechanism you can use for converting rotary motion in the crank to linear motion in the slider. If the crank center line and the slider center line are lined up on the same line, then when that crank stretches all the way out as far as it will go, and then it turns back around as short as it will go, the distance that slider follows is twice as long as the crank is. And we'll look at this in CAD. We'll look at a drawing and kind of fool around with how we can visualize that. The distance that the slider follows is called the stroke, and you can see it at the top of the slide here. There's a dimension on the stroke from the very leftmost position to the very rightmost position. If the crank and the slider are not in a line, then the stroke is not exactly 2 times the crank length, and it's just some odd number, and you just have to do your schematic to figure it out. That's what you will do in problem 4 of this assignment. And your problem 4 is set up kind of like this picture, this schematic in the lower left corner of this slide, although this is not technically a schematic. Here are the 4 problems in assignment 13 that you'll be working on, and in each of these he gives you some lengths and he asks you to draw a schematic of the thing. In the first problem, he gives you the lengths of the links in a particular size of vice grip, and what you are going to do is draw the schematic of the vice grip and figure out when it's all the way in the far right position, where will it be, and when it's all the way in the far left position, where will it be. And in CAD we'll look and see how do you do that. You will not draw a working drawing or a pictorial for any of these. These are just put in here to be illustrative, to be helpful. All you will draw is the schematic for each one. Here's the second problem, one of these clamps, and again, like a Destaco, for example, you'll not draw the clamp, you'll just draw the schematic. And notice in both problem 1 and 2, those 2 fixed lengths are not in a line. They're kind of offset a little bit. In problem 3, those 2 fixed lengths are in a line, and what's a little bit different about this problem is he asks you to figure out how many degrees is the angle through which this rocker CD will oscillate. How many degrees is it? I think it's 86 degrees, as I recall. Then problem 4 is a slider crank. So here is the crank AB, and it's going to go round and round in a circle. Oops, sorry. Here is the slider, and it's going to move in a linear fashion back and forth. What he shows you here is an intermediate stage, so it's not all the way extended and it's not all the way pulled back. He just tells you, well, when it's sitting at this position, here are some numbers. And from there you can figure out how to lay out your crank and slider. So for now, what you could do is open a title block, and following the sizes that he gives you in the assignment, just begin to set up your drawing. Figure out where those fixed links need to go. See if you can get a crank drawn in there somewhere, maybe. Anything else you can figure out how to put in there, do that. And just to repeat, this is out of our book again, remember that our goal is when your drawing is printed, we want that pin joint to be about 3/32 of an inch in diameter, more or less. There is not an ASME standard for these, so this is more conventional practice than anything else. And when you're laying out your 3 problems, let me back up. There are the 3 problems. Now I'll go forward. Try to imitate these proportions that he shows us as best you can. Now there are no set dimensions, so just do the best you can, but try and make that ear about that relative size relative to the 3/32 circle, and put a little bit of hatching on the ground underneath it.